Welcome to part one of our lecture video series for Friday, May 12th, where we are going to discuss why water is such a unique substance based on what we know about the intermolecular forces that exist between water molecules. So let's start by comparing the phase diagram of water, which is shown here on the right, to kind of like a typical or expected phase diagram for a substance here on the left. So looking at the substance on the left, we expect to see some kind of curvature upward. And then in particular, we expect to see this like slanted up and to the right line, kind of pointing in this direction, at least overall, for the boundary line between our solid and our liquid phases. So that's line B. However, if we compare that to what's going on in water, we see that the line between our phases that are our solid phases and our liquid phases trends backward. And what we're going to try to do is we're going to try to explain this. So why is it that at low temperatures and high pressures, solid water exists in a smaller temperature and pressure window range. So why is it that this is a lot smaller for water, right, compared to something like this for another substance? And the answer comes to us from the fact that water is less dense as a solid or ice compared to its liquid form. We've all seen this before, right? We have seen ice floating in a beverage, right? If we've got ice water, we know that that ice is floating. And that is because the relative density of solid water compared to ice, or excuse me, of ice compared to liquid water is lower. So I'm able to have ice float in water because the ice is less dense, whereas the liquid water is more dense. So why is this? Why is this something that happens, right? This is kind of really unique to water. What's going on with water? Like, what is it about the water molecule that allows for this to happen? So let's remind ourselves about the structure of water. So recall the 3D structure of water. So water is one of our polar compounds that has a bent geometry where we have a local electron geometry of tetrahedral. But because two of those electron groups are lone pairs, we see an overall bent shape, which is what makes water polar. So I could draw these dipole moments along each of my covalent bonds between hydrogen and oxygen, where I have a region of partial negative charge up near toward that electronegative oxygen, leaving behind a partial positive charge near down the bottom of the molecule toward our hydrogens. Now, it's these dipole interactions so interactions between the dipoles of water that give rise to water's kind of unique properties. For example, we've discussed at length how the polarity of water allows it to act as kind of a universal solvent. But what is it about like water's polarity in particular that makes it so special? So let's remind ourselves about what's going on in terms of intermolecular forces. So from an intermolecular forces point of view, we of course have our dipole-dipole interactions. So we have our van der Waals interactions, but remember, we have here a special type of dipole-dipole interaction that only results when you have a bond between our very electronegative elements, oxygen, fluorine, and nitrogen, and something like hydrogen, and hydrogen, not something like hydrogen, just hydrogen. So anytime we have a bond between oxygen, nitrogen, fluorine, and hydrogen, a very, very strong dipole-dipole attraction and repulsion is established. And this has a special name. So this very strong dipole-dipole interaction as a result of a bond between oxygen, nitrogen, fluorine, and/or hydrogen. This is what we call a hydrogen bond, or the hydrogen bonding intermolecular force. So it's not like an actual bond that's being formed, but it is a really, really, really strong electrostatic interaction between these water molecules. So again, let's go back to this phase diagram of water. Why is it that the hydrogen bonding that's present in water allows for us to have a solid substance that is less dense than its liquid phase? So what we're going to do is I am going to actually bring us to a web page. All right, so let's remind ourselves about what's going on in liquid water. So all of our molecules are moving in kind of like this constant random motion, and they are occasionally attracted to one another via these hydrogen bonds, which are shown here in green. So you can see these little green dashed lines showing the strong dipole-dipole attractions between our water molecules. If you want to zoom in on what that kind of looks like between just two water molecules, it would look like this. It's called the water dimer, 2-di. So we've got that partial positive on a hydrogen attracting to a partial negative on the oxygen. And scaling this up down here in liquid water, right, we see that on the whole, we have a bunch of those, but overall, like the three-dimensional organization of our water molecules, due to the fact that they're just moving around a lot more faster, there's kind of a lot more chaos in our system, is going to be less so, right? We have less structure, less overall organization of our water molecules, meaning we have not maximized the number of hydrogen bonds that could occur between our water molecules. So for example, like if you look at this top region here, yes, this top region has hydrogen bonding between those top two molecules, but then toward the center or here, kind of now up and to the right, we see that that water molecule kind of in the middle of right corner is not hydrogen bonded to any other water molecule, and that's just because statistically the position of it in three-dimensional space in this sample of water was not one that allowed for it to encounter another water molecule and establish that hydrogen bond. Now, Let's think about ice, right? Ice is water that has been cooled. So if we start transferring a lot of thermal energy out of our system, or a lot of heat out of our system, then our molecules are going to gradually start slowing down. And as they slow down, they're able to eventually lock into place. And the means by which they lock into place is one where you have this overarching structure where for every water molecule, there's this associated other four water molecules that each molecule's hydrogen bonded to. So we can kind of look at any one of these molecules and we can see that it is 1, 2, 3, 4 attached to four of its counterparts via hydrogen bonding. And notice this large scale organization, due to our molecules just moving slower and eventually being kind of clicked into place by these attractive forces, is resulting in there being a lot of space between these water molecules, right? Look at this structure. There's a lot of general like open space found between our water molecules. They are not as tightly packed because of those hydrogen bonds giving us this overarching organization compared to the liquid phase, where we have this kind of occasional untethering between molecules that allows for them to get close to one another, where we have these kind of hydrogen bonds that are set up and then not set up as a result of the movement of those molecules. So we can kind of cluster molecules together in a more chaotic array compared to the structure of ice. So it's because of that hydrogen bonding, we have this overarching structure in ice that allows for there to be more space between those water molecules. And that's what results in us having this less or lower density in the solid phase compared to our liquid phase. And this is why the phase diagram of water has this trend backward for the phase boundary line between liquid and solid. So interesting case to see how these intermolecular forces are not only like demonstrated in everyday phenomena that you and I could witness, but explain also overarching trends in how a substance behaves, looking at things like its phase changes or overall just even its phase diagram. So now that we have considered kind of the uniqueness of water, let's go over intermolecular forces kind of in general, and let's look at intermolecular forces in conjunction with the size, shape, or mass, or even surface area of a particular molecule to try to predict things like trends in boiling point, vapor pressure, or melting point. So we were able to kind of predict trends in the phase diagram of water here based on knowing that hydrogen bonding is present in water molecules. Now we are going to look at intermolecular forces like hydrogen bonding and others, in addition to other molecular properties, to see if we can't get more information about those physical properties of our substances. So that is coming up in part 2. Next.